Hello, my name is Keenan Maxfield. I am an instructor for Solar Energy International, and I would just like to share with you some of the basics of AC electricity. This is a topic that many people kind of know, but they don't really understand. And while we can do our jobs without really understanding it, I find it very helpful to understand how AC electricity works, especially when we start talking about three-phase electricity. Most of you are familiar with this graph here, but how many of you really understand what it means or how AC really works? Let me point you to an illustration. When electrons travel in an alternating current, they're essentially going one direction for a short period of time, and then they turn around and travel in the opposite direction. Think of those old two-man saws. They work by moving the blade back and forth, etc. Now with 60 Hz AC voltage, the direction is switching 120 times per second. I drew a little graphic to show this. I'll give you a moment to read this graphic, but as you can see, when the sine wave is at its peak, the voltage pressing in one direction, but when the sine wave is at its trough, the voltage is pressing in the other direction. And as the sine wave is crossing that horizontal line, there is no voltage. So as you can see, the horizontal axis represents time, and the vertical axis represents voltage. So at this point, we're at 120 volts. And at this point, we're at negative 120 volts. And that gives us our 120 volt AC power. When we add the second leg on a split phase system, it goes the opposite direction. And now if we measure from here to here, we see that we have 240 volts. But again, it's hitting zero, 120 times per second. So now when we have three-phase power, it looks more like this. And you can see that on each wire, we have the same simple sine wave where it's going positive voltage, negative voltage, but they're all offset. So at any one given point in time, we have power between the legs. Now you can see that each leg has 120 volts to neutral, but because the legs are offset from each other, the voltage does not add to itself like it does in 240 split phase. This is because these other legs are not at 120 volts to neutral when that other leg is. When we're measuring voltage phase to phase, we're only dealing with two of the phases, so for simplicity, let's get rid of that third phase. So let's just say we were measuring from the black wire to the red wire. You would see that right here we have a negative voltage because the red wire is below the black wire. And if you're measuring the distance between these two sine waves, between these two phases, you would see that as we go along, that distance is getting greater and greater and greater. Here, the distance from there to there is greater than back here. And you'd see, if you're looking at this with a ruler, they'd be getting further and further and further apart until we reach somewhere right in here where this one's approaching its hump and this one is leaving its hump. At that point, the wires actually start, or the phases actually start coming closer and closer and closer together. Now, again, this is voltages. The wires themselves are not actually moving, but the voltage potential is getting closer and closer and closer to each other until they cross right here, and there's zero voltage difference between the two wires. And then again, they start going further and further apart. This time it's a positive voltage because the red wire is above the black wire. We're measuring from the black wire. And it's getting further and further and further apart until this one starts to approach its hump and the red wire is starting to leave its hump. And so on, getting closer and closer together till again we reach zero and they start going further apart again. So if we were to draw out the difference between these two wires as an additional sine wave, this would indicate the voltage between the two wires. Again, measuring from wire to wire. And it would look like this orange line. Here, the black line would represent the black wire because, again, we're measuring the distance from the black wire. and the orange line would represent the voltage difference between the two wires. So as you can see, the greatest voltage difference is right in here, where that one's leaving its hump and that one's approaching its hump. And there's zero voltage difference here, where these two lines cross. And then again, there's greatest voltage right up in here, where this one's just leaving its hump and this one's just approaching its hump. Again, there's zero voltage difference here, where those two lines cross. So if we're only looking at the voltage from line to line, or from phase to phase, it would look like this sine wave here. Now you can see that this voltage here is greater than these voltages. It's greater than 120 volts. Again, we're sticking with the 120 volt system for now, although this all applies to other voltage systems. But this here is greater, but it's not double. You can see if it were double, this would be much higher. But anyways, this ends up being approximately 208 volts, assuming that this is 120 volts. Now it just happens that all of these voltage relationships correspond perfectly with the relationships we find in triangles. Even when we fully understand what these sine waves represent and how AC electricity works, the sine waves can still be quite confusing sometimes. For this reason, it is often helpful for us to think of three-phase power in terms of triangles. These four dots represent the four wires in a three-phase Y system. Now, I have not been sticking to any traditional wire coding standard, and this is no exception. I am trying to use colors that make sense and contrast well so that you can see them. Here I'm using red, orange, and brown to represent my three phases, and I'm using the blue dot to represent the neutral. I figured if I used a white dot, you wouldn't really be able to see it. I spaced the three phases perfectly evenly from each other, and I placed the neutral exactly in the center of the triangle. If we measure the distance from the neutral to any one of the phases, we will see that they are all exactly the same, and they are all exactly 120 units. Now this could be 120 volts, could be 120 millimeters, 120 inches. In this case, I actually spaced them 120 pixels apart to make it easier. Now if we measure the distance between the phases, such as these black lines here indicate, we will see that the phases are all exactly the same distance apart. Now we could do a bunch of trigonometry in order to calculate the distance between these phases, or we can go online and use a triangle solver. Or, if we drew it to scale right, we can simply measure the distance between the dots. In this case, the distance between the dots happens to be 208 units apart. As you may remember from just a few moments ago, in a three-phase Y system, if each phase is 120 volts to neutral, the voltage from phase to phase will be 208 volts. So the relationships we find in the voltages are exactly the same as the relationships we find in the triangle. Now, a three-phase delta system is exactly the same, except for we don't have a neutral. Now, when I say that, I mean a standard three-phase delta system, such as a 480 three-phase delta, where there is no neutral at all. There is a three-phase delta system that is called high leg or stinger leg that we will be discussing, and that is an exception. That does have a neutral in it. But with a standard three-phase delta, it's just like this with no neutral, and often the voltages will be different, whether it be 480 or something like that. Here is another delta three-wire configuration. Now in my experience, three-wire delta configurations are quite rare. The Y configurations are by far the most common form of three-phase power. The last three-phase power we will talk about today is the four-wire delta configuration. This is relatively uncommon, but it is actually much more common in my experience than the three-wire delta. This configuration is most common in older light commercial as well as in large ranch homes, where they require three-phase power for the ranch, but they also want to supply the home off of the same service. It is often called the high leg or the stinger leg configuration. Now you can see that the neutral here is this blue dot, and it has been placed in between phases 1 and phases 2, or the red phase and the brown phase. The voltage from any phase to any other phase is 240 volts, and the voltage from phase 1 or from phase 2 to the neutral is 120 volts, but the voltage from that orange phase to neutral is different than the voltage from the other phases to neutral. Let's explore what is actually happening in these voltages and see if we can figure out what the voltage from the third phase to neutral would be. For a minute here, let's just look at the red wire, the neutral, and the high leg, and let's forget about the rest of the triangle. Let's think about this for a few minutes in terms of voltage from the red phase. The neutral is 120 volts from the red phase, and the orange phase is 240 volts from the red phase. If our red phase is our reference point, our sine waves would look like this. Now I'm sorry the colors aren't quite the same. The red sine wave here would represent the orange phase. That black sine wave would represent the neutral, and since our red phase is our reference point, that would be the flat line at 0. You can see that the red phase is twice as tall as the black one. So if we were trying to see the voltage between the neutral and the high leg, let's see how far apart the two sine waves are, and let's see if we can see a pattern. So you can see here the two sine waves cross, and so there's no voltage between them. But as we go along, they're growing further and further apart. And down in about here, if we're looking at this with a ruler, we can see that this right about here is where they're about the furthest apart, vertically speaking. But then as we get past that point, they start getting closer and closer together, until again we reach right here where there's 0 distance between them, and so on. Now if we were to draw the distance between these two phases, it would look like this. So now that we have that visual, you can see that this orange sine wave represents the distance from the black wave to the red sine wave. Here, where the red sine wave starts to dive below the black one, you can see that the orange sine wave is at 0. And then continuing along, right in here where the red sine wave is the furthest away from the black sine wave, you can see that the orange sine wave is at the bottom of its trough. And then again up here where the red sine wave crosses the black sine wave, again the orange sine wave is at 0, and so on. You can see that the orange sine wave is larger than the black one, which was 120 volts, but is smaller than the red one, which was 240 volts. It happens that the orange sine wave is 208 volts. Now let's go back to our triangle. Here again you can see that the high leg is 240 volts from the red phase, and the neutral is 120 volts from the red phase. If you have drawn out the original triangle to the correct scale, with each side being 240 units long, and then cut the triangle in half as we did here, you could measure the distance between the high leg and the neutral point, and see that it is exactly the same as the voltage. We could also calculate it mathematically. You could use the Pythagorean theorem to solve for the unknown side, or you could use sine, cosine, or tangent if you are familiar with trigonometry, or you could just go online and use an online triangle solver. Any way you do it, you should get a result of approximately 207.846, or approximately 208. Again, we can see that the relationships in triangles are exactly the same as the relationships in three-phase power. I hope that this has helped you to understand how exactly AC electricity works and to understand the three-phase configurations.